Okay, in today's lesson we're going to be talking about displacement, velocity, and acceleration in two dimensions. In the last unit, we studied motion in one direction. We looked at objects moving in the x and the y directions separately. In reality, this is quite limiting. In this unit, we will combine both directions to study motion that will be moving in both the x and the y at the same time. It may sound confusing, but in reality, we really have all the tools we need to solve these problems. But as you can see, you may need to go back and review vector operations and the one-dimensional kinematic equations. All right, so let's get started. First, let's look at displacement that happens in both the x and the y. All right, so we have some initial position, RO, some final position, R, and a change in position, R final minus R initial would be equal to displacement. So how is this any different than the last time? Well, the last time we either went in the x or in the y. In this case, it's going a little bit in the x and a lot in the y, so it's doing both at the same time. And I also wanted to put a little note here that this diagram is not like adding vectors the head-to-tail method. It's just showing the final and the initial and the change between the two. All right, so now we know displacement. So once we have displacement, we can get the idea of average velocity. This is just taking the displacement and dividing it by the elapsed time. And it's no different from the last time. But now this component of displacement may have some amount in the x and in the y. As you can see here, some in the x and some in the y. All right, how about instantaneous velocity? Well, we know that instantaneous velocity indicates how fast a car is moving and the direction of motion at each instant of time. So, let's say you're going on a turn, and what's the instantaneous velocity at this point? In other words, at this point, drawing a tangent to it, which direction would it go in? And how fast would it be going in? That would be the instantaneous velocity. And once again, it's really the same equation, but this time has a limit of delta t approaches 0. And this hasn't changed since the last chapter. And once again, here's our definition of average acceleration. Has this changed? Well, no. It looks exactly the same. But now you can have some of the velocity in the x and some of the velocity in the y. And once again, a little disclaimer that this is not the head-to-tail method. Now you might say to yourself, well, if it's still going in a straight line at this point, why don't I just take the normal xy axis and rotate it, and then it would only be in one direction. And the answer is, well, you can do that. But how about if in a problem it's constantly changing? You can't keep on changing your axes, such as throwing up a ball in the air like projectile motion. It's constantly changing, so you couldn't just rotate the axis. Okay? All right, so here's our equations of kinematics. And you may be saying to yourself, so what's the difference? And there really isn't any. But now what we're going to do is look at some of these. Like this velocity could have a component in the x and in the y, so could this, so could this. The only thing that can't have a component in the x and in the y is time. So we can treat each of these independently of each other. So let's look at that with an example. Let's look at the x direction of a plane. It could have an x acceleration. It can have an initial position, a final position. It can have an initial velocity and a final velocity. So it can have all the original kinematic equations, but this time with the subscript x. Notice t doesn't have a subscript because time doesn't have any x or y component to it. It's just a scalar. Okay? All right. So is this true with the y direction? Well, let's look. You have a plane that could take off vertically. So it has an acceleration going up. You have an initial velocity in the y, a final velocity in the y, initial position in the y, final position in the y. So all those equations are completely the same. So what's the difference then? Well, let's look at this problem here. We have a plane that's accelerating in both the x and the y. They both have an initial velocity in the x and in the y. And they have an initial position in the x and the y. And what we're going to do is we're going to solve each of them independently, because the motion in the x has nothing to do with the motion in the y. All they are is related through time. Okay? So, here's the problem. In the x direction, the spacecraft has an initial velocity component of 22 meters per second and an acceleration in the x of 24 meters per second squared. And in the y direction, the analogous quantities are 14 meters per second and 12 meters per second squared. At a time of 7 seconds, we want to find A, the final position in the x and the final velocity in the x, and B, we want to find the final position in the y and the final velocity in the y, and C, the final velocity of the spacecraft altogether. Alright, so we're trying to find the x and y position, the two components of the speed, and the final speed. Alright, so how should we do a problem like this? You should definitely make a drawing. You have to decide which way is positive and which way is negative. And then obviously you're going to write down all the variables that you have for each direction. Verify that the information contains values for at least 3 of the kinematic variables, as we did in the last unit. And you do this for the x and the y. And then you're obviously going to pick the appropriate equations to solve for the unknowns. And when problems are broken into multi-parts, you would use like the ending value of one part for the initial value of the next part, just like we did in the last unit. And also, there may be more than one answer when solving some of these problems because of taking squares and stuff like that. Okay, so back to our problem. What we want to do is make a table for the x and the y's. Okay, and take a moment to see how these tables are set up and how they do have each of the components that were given in the problem. For example, AX, 24, 24. V initial in the X, 22. And time 7 seconds. Notice the time is the same between both the X and the Y, because once again time doesn't have a subscript because it's only a scalar. Alright, so now let's look at the X direction. Notice none of the Y direction components have anything to do with this because X and Y are completely independent. And here we solve for how far it will go in the X using only the X numbers. Initial velocity times time plus 1/2 the acceleration of the X times time squared equals 740 meters. Okay. And the final velocity in the x takes the initial velocity plus acceleration times time is 190 meters per second. Alright, now in the y, it's actually going to be the same equations because the same information was given to us, but just x and y. And here's the answers in the x and, now in the y. You can see what the y position will be and the speed in the y. Alright, so we did parts A and B. Now let's look at C, where we're combining the two together. So we have an x velocity of 190 meters per second, a y velocity of 98 meters per second. And we're trying to find this final velocity. But this final velocity will have a magnitude and a direction. So the magnitude using Pythagorean's theorem comes out to be 210. And the angle comes out to be 27 degrees. So the final velocity would be 210 meters per second at an angle of 27 degrees, in this case, north of east. Okay, so you can see that the x and y positions were solved independently of each other. The only thing that really they had in common was the time, okay? Because the motion happened for the same 7 seconds in each direction. So I just wanted to really point out the fact, or reiterate the idea that they are independent of each other. So it's not like you've learned anything new. It's just that now you're breaking down motion in 2 dimensions into independent x and y's, solving the x and y's, and then coming back together at the end of the problem to come out with a total velocity or a total displacement. Matter of fact, for this problem, we could have actually found the total displacement as well by taking the two answers here of 390 in the y and 740 in the x, and excuse me for paging through like this, and did the same idea here as we did here with velocity. We could have done the same thing with displacement. Okay? In the next section, we're going to be talking about projectile motion, which is going to be treating the x and y's independently once again, but it's a little bit more of a common problem of like shooting something. Okay?